Dr. Dave Pearson is originally from Southern California. He went to the University of California, Santa Barbara, graduated Bachelor of Science with honors in geosciences. He then spent 3 years working in the environmental geotechnical consulting industry, interned with ExxonMobil, went back to school, earned a master's and PhD, also in geosciences from the University of Arizona. He's currently an assistant professor at ISU, and when you look, he's teaching, it seems like every course they have. His actual research expertise, structural geology and thermochronology, isotopic dating of minerals. He's very much interested in the regional scale tectonics, including how continental mountain belts grow, which we are more or less have to our south and to our north. Also the structure and tectonics of the northern Rocky Mountains, Utah, Wyoming, Montana. He has over 20 plus professional papers to his name, which is an awful lot considering he hasn't been at it for that long. Numerous awards, scholarships, and honors, which I will not mention. Please join me in welcoming Dave Pearson.
Can you hear me? Is the microphone on? No?
No. We'll speak into the microphone.
All right, well, the light's on. Can you hear me a little bit better?
Yeah.
All right. Well, thanks for the invitation to come out here, and thanks everyone for coming. I am going to talk about, so the title of my talk is Building Mountains in Old Continental Crust. So I'm fundamentally interested in how continental mountain belts grow. And I'm going to tell you about some work I've done in what I consider 2 natural laboratories in the southern central Andes in Argentina and Bolivia, as well as in the northern Rockies. So mostly focused in Idaho, southwest Montana, western Wyoming, and northern Utah. Before I get started, I wanted to acknowledge some former students and current collaborators, as well as funding from U.S. Geological Survey, ExxonMobil, National Science Foundation, and Idaho State University. So the photo that I have up here is kind of going to set the stage for one of the main things I'll be talking about today. And this is a view of one of the big mountain ranges in northern Argentina. It's called the Capchi Range. And you can see the highest peak over here is over 20,000 feet. And these rocks over here, this is going to be a theme of my talk, these rocks right here are Cambrian in age, and they're sedimentary rocks, or metamorphosed sedimentary rocks. And these have been, you can see I've overlain some map symbols on here. And what this shows is that these metamorphosed sedimentary rocks have been thrust on top of these much younger rocks that are late Cretaceous in age, so 70 million years old, something like that. And so I'm going to talk about this particular structural style, which involves basement type rocks and involves thrusting of those rocks on top of younger rocks. All right, so Mike said I didn't need to give you a refresher about plate tectonics, but I'm going to anyways. And so just to make sure we're all on the same page, so the theory of plate tectonics, pretty straightforward. The surface of the Earth is covered by these semi-rigid plates that are moving around relative to each other, and there's different ways that they can move relative to each other. They can either be moving toward each other at these convergent plate boundaries, and at these convergent plate boundaries, one plate is commonly under thrust beneath the other one. That's called a subduction zone. And associated with these convergent plate boundaries is formation of a volcanic arc on the upper plate, and oftentimes deformation, shortening of this crust on the upper plate. This is in contrast to where plates are moving apart, which we call divergent plate boundaries. An example of this is in the mid-Atlantic, where you have the North American plate moving away from the Eurasian plate and the South American plate moving away from the African plate. And what happens here is that there's melting of mantle material in here, and eventually you form a new plate right between where those two plates are pulling apart. So that's a divergent plate boundary. And the last plate boundary is a transform plate boundary. It's kind of a subsidiary plate boundary, but they're really important because There's a couple of transformed plate boundaries that are near big population centers, such as in Southern California, on the North Island of New Zealand. And so these are areas where plates are simply moving past one another, but they present big seismic hazards potentially to some places that are located adjacent to them. So these, at the margins of these plates where they're moving toward each other, moving apart from one another, the crust is subjected to stress. So in some places, the crust is subjected to compressive stress, and that results in formation of faults. And faults are fractures where one side is slipped relative to the other side. So this particular type of fault right here, where the upper part has moved upward relative to the lower part, that's called a thrust fault. And you can see that accommodated some crustal thickening, so it's thicker there than where it used to be. And it also accommodated crustal shortening, so it's shorter in that dimension than it was when it started off. And that's different from a normal fault, which essentially this upper part moves down relative to the lower part. It gets longer in a horizontal direction, so these types of faults accommodate crustal extension and vertical thinning of the Earth's crust. And I'm going to focus on these thrust faults today. And in particular, I'm going to look at convergent plate boundaries. There's oftentimes a series of thrust faults that forms in the upper plate as a result of the horizontal compressive stress from this plate pushing against this overriding plate right here. And you can see here's a zoomed in, very simplified view of what some of these thrust belts, we call them, fold thrust belts, of what these might look like in cross-section. This is kind of an oblique 3D cross-sectional view of them. And I'm going to focus on a lot more details of how these thrust belts work. But basically, these thrust belts are the main mechanism that big continental mountain belts form. So I'm going to start off really zoomed out, and then I'm going to zoom in a little bit more. So this is a really simple image, but someone that's interested in how continental mountain belts grow, this gets them really excited. So this gets me really excited. And a couple of reasons why. So you can see the topographically high elevation areas. You can see over here in the western side of North America and South America. You can see over here in the Himalayan mountain range continuing into the Middle East and all the way through Europe. You can see a couple of areas, really long, curvilinear belts of high elevation mountains that are forming adjacent to plate boundaries. So here is a continent-continent collisional boundary in here where Africa and India are colliding with Eurasia. And over here in South America and what used to be happening outboard of western North America, there is an oceanic plate. This is called the Nazca Plate down here. It used to be called the Farallon Plate over here. But there was an oceanic plate that was subducting down beneath western North America and forming this big, long, linear chain of mountains. All right, so why do we care how continental mountain belts are formed? There's a lot of reasons, and one reason might be because they're beautiful. And so this is a photo of the Patagonian Andes, which is one of the most beautiful mountain ranges on Earth, in my opinion. But there's a lot of really important societal implications for how mountain belts grow. One of them is that the biggest earthquakes that we've had in historical times are associated with convergent plate boundaries, and continental mountain belts have some of the largest earthquake hazards and landslide hazards that we know on Earth. They're also fundamental localities for forming and preserving and exploring eventually and exploding mineral and petroleum deposits. And so, for example, in the Zagros in the Middle East, that's an area where all those prolific hydrocarbon deposits are. That's a convergent plate boundary, and that's a fold thrust belt that's prospective for oil and gas. And so, understanding how the mountain belts grew is really important for identifying these mineral and petroleum deposits. There's also some other reasons. So, you can imagine, climate is controlled by atmospheric circulation. And so if you're poking something that's really high up into the atmosphere, it's actually deflecting the atmospheric circulation. And so people have talked about how the Andes and the Himalayas have actually influenced the climate on Earth. So there's a climate spin on there as well. And something I'm really interested in, more of an academic reason, something I'm going to talk about today, they're really important localities for forming new continental crust. So this is a question that geoscientists have, kind of an ongoing question. How is continental crust formed? Well, we know that new crust is formed at these convergent plate boundaries, and there's a lot of crustal shortening and thickening and melting and metamorphism that's happening in there. And so that's redistributing that continental crust, and it's kind of refining it. And so I'm going to talk about some of the details of that reworking process. And I didn't mention, if there's something that you have a question about, if you want to interject, if you think that I need to clarify, you're welcome to do that throughout this talk. All right, so getting into a little bit more detail, thinking about thrust faults and thrust belts, which is what I'm going to focus the rest of the talk on today. I wanted to take us back to some of the early work on understanding thrust faults, in particular by Rich, who published a paper in 1934, who recognized that these thrust faults, so here's a cross-section in the Appalachians. You can see the thrust fault is shown in here in this thick, bold line. You can see the thrust fault, something he recognized was that the thrust fault follows some really weak stratigraphic horizons. And so it seems to be parallel to these really weak shales, so kind of gooey, clayey sedimentary rocks. And then it forms these ramp intervals in the more strong sedimentary rocks. So people recognized very early on, when we were starting to understand fold thrust belts, people recognized early on that these pre-existing weaknesses, so in this case it's actually a stratigraphic interval that the thrust faults are exploiting, these pre-existing weaknesses are really important for controlling thrust belts. And so this is something that I'm going to reiterate throughout the talk today, and this is going to be a fundamental conclusion that I make at the end. People also recognize, so there's another author who published a paper in 1921, Griffith, who recognized that in the lab, rocks are we expect that they should be much, much stronger than they really are. And so basically we expect that they should be really strong, but when you deform them in the lab, they end up being a lot weaker. And so what he proposed is that at all scales, at a microscopic scale, there's little micro cracks that are preferentially oriented within all materials and in rocks, which is what we're concerned about now. And with deformation, and in this case, it looks like kind of a wedge that's being jammed into a pre-existing slice in some material. With deformation, those micro cracks will link up, the favorably oriented ones will link up, and they'll form a through-going fracture. So I'm just trying to drive home the point that existing weaknesses in rocks are really important for controlling how rocks deform. And this is something that we've known for a really long time. All right, so so this is what structural geologists like to do, look at mountains in cross-section. So I'm going to be showing a lot of cross-sections here. So essentially if we could just slice through the earth, this is an interpretation of what it would look like. And there's three main mountain belts that I'm going to talk about here briefly, just to show you some of the main features that we observe in all these mountain ranges that they have in common. So the upper one up here, you can see this is in the central Andes, and this one is in southern Bolivia, and right at the border with northern Argentina. And what you see, there's a couple observations, but fundamentally what you see is that all of these thrust belts have kind of a wedge shape. And so this one, the high elevation, this would be the high elevations of the Andes over here on the left side. This would be the lower elevation on the right. And then this lower layer right here, all these sedimentary rocks are detached from the basement along a fault that slopes to the left or to the west in this case. And so overall they have kind of this wedge-shaped geometry to them. And you see that for all of these mountain belts that I show up here. You also notice for all of these mountain belts that the older thrusts are almost always in the central part of the mountain range, and the younger thrusts are almost always in the frontal part of the mountain range. So that's true for all of these, for the most part. That's true for all of these cross-sections that I show up here. And another fundamental observation is that all of these in here, for the most part, again, but almost all of these in here, they involve deformation of sedimentary rocks that overlie basement. And so we call this, when these are being deformed above the basement and the basement is not deformed along with the rest of the fold thrust belt, we describe that as being detached. And so I'm going to talk about detachment horizons within these fold thrust belts, and that's going to be one really important take-home from this talk. But three fundamental observations: they're wedge-shaped, they young toward the front, and they're mostly detached from the basement that they overlie. All right, these observations led to a really interesting and and useful model for how these mountain belts grow. And it's really cool because I can go into my structural geology class and I can get out a little sandbox and I can demonstrate to the students that there are some very good similarities between real mountain belts and just a typical pile of sand that I'm putting in a little sandbox and cranking the end to. And what you notice is that, so you can think of this as, today's sake, there's not much snow out there, but you can think of this as snow on the ground in front of a snowplow. And basically what happens is this theory called critical taper theory. What happens is that one side, so this is a layer of sand in here, one side is being moved relative to this basal part of the sand layer. And what happens is that you end up forming a wedge shape. And so as you push from the left, this ends up forming a relatively steep wedge shape in here. And the wedge is defined by the slope of the surface and the dip of this basal portion of the wedge in here. And so this was true of most thrust belts, like I just showed you. Many thrust belts have this wedge shape. But what's really interesting about this is that these authors, in particular Davis and Suppy and others, they noticed that this wedge seems to grow with a similar angle at the surface through time. And so in other words, this wedge right here, so imagine this is a snowplow, it's incorporating, you're pushing this over in this direction, it's getting thicker in here, but imagine this point stays fixed. This is going to get a little bit steeper, but once it reaches the angle that it prefers to be at, which is in relationship to the material properties and the friction on the bottom, it'll actually continue propagating and grow self-similarly at the angle that it prefers to grow at. So in other words, this is getting steeper right here, but it doesn't like to be that steep. So what it'll do to decrease the steepness is it'll incorporate new material over here and decrease the surface slope of that wedge. And then maybe this is not as steep as it likes to be. So in this case, it would internally thicken this portion over here, steepen up the taper to the angle that it likes to be at, and then continue to propagate to the right. So this was really interesting because it suggested that there were two really important factors that control thrust belts. By analogy, these sandboxes to thrust belts. One was the compressive strength of the material. So you can think in the sandbox, fundamentally it's kind of like the cohesion between the sand grains. And what's also really important is how strongly coupled the base of the sand wedge is to the underlying material. And so those two takeaways, those kind of were put forward as some really important contributing factors to understanding how real fold thrust belts grow. And so here's, and I never have a model that's this nice in my classroom, unfortunately. But this one is really cool. And so you can just kind of be mesmerized by this. It's just going to loop back and forth. But what you'll see is that, and what we think these are really good ways of understanding thrust belts to first order. And so what you see is that, this, just like I said, this kind of has a wedge shape to it. It kind of maintains the same surface angle as it continues to incorporate new material into that wedge as it moves to the right. The younger thrusts that are forming in here, you can see from this red marker layer, the younger thrusts are on the right side. So that's consistent with how real thrust belts behave. Most of the structures are on the young, kind of low elevation portion of the mountain range. And the sand is detached from the underlying substrate. So that's just like in the real thrust belts that I showed you about in a couple slides. It turns out that I think this is a great first order model of understanding thrust belts, but anyone that looks at a real thrust belt, this doesn't look like a homogeneous pile of sand. What you notice is that there are these distinct thrust horizons, and they oftentimes form parallel to sedimentary layers. And so there's this mechanical anisotropy, or in other words, layering within the sedimentary rocks that the thrust belt is deforming that are controlling the geometry, the internal geometry of the thrust belt. There's a couple other reasons why I think in detail that these probably aren't the best way of understanding thrust belts when you get into more detail. One of them was pointed out by John Suppy, who's a really well-known geologist who worked on critical taper theory, and in particular was really interested in the Taiwan fold thrust belt. And so he's done a lot of work in Taiwan, and that's one of the best modern analogs that we think these sandboxes can compare to. And what he found, it's really interesting, if you plot the alpha angle, so that's the surface angle, and the beta angles, so that would be, here's your sandbox experiment right here, here's a wheel, and sand is just kind of being incorporated into that wedge in there. If you plot these angles on here, look, it has a pretty steep slope, pretty steep negative slope. And if you compare that to the real slopes in Taiwan, for example, you see that it's much lower. And in particular, these alpha angles, so the surface slope of the Taiwan fold thrust belt is much, much lower than you'd expect compared to these sandbox models. And so what that suggests is that, kind of getting back to what I pointed out, I guess, here, a shallow surface slope usually means that there's a weaker horizon at the bottom and less frictional coupling between this material and this material down here. So what these results suggest from the Taiwan fold thrust belt is that the rocks within the Taiwan fold thrust belt are substantially weaker than we'd expect if we use these sandbox models. And so I think that's important. So what I think is, even though I think critical taper theory is really useful, I think there are some shortcomings, and in particular it has to do with the fact that there are a lot of detachment horizons within the thrust belt. So these areas where thrusts glide along parallel to the stratigraphy, the sedimentary units, and these are actually controlling the geometry of the thrust belt. And that's what I'm going to focus the rest of my talk on right now. You'll see that, in particular, some finite element models from Stockmall and others show the same exact thing. So it's really tough to duplicate any real-life thrust structures with the models unless you impose these horizontal weak layers within the thrust belt. So it's really important to have these weak stratigraphic horizons essentially within the thrust belt to get the geometries that we see. All right. You'll also see that if you look at globally, and so here's an example from South America. If you look globally at the geometries of thrust belts and cross-section, what you'll see, so here's Bolivia right here, here's a little map of Bolivia and a cross-section across southern Bolivia. You'll see that this looks very similar to the examples of thrust belts that I was showing you previously. It looks like the thrusts are, they're mostly dipping toward the left in here, toward the interior of the mountain range. They don't involve basement, which is this gray stuff down here at the bottom. So there's some similarities with the real, with the thrust belts I showed earlier. But if you go farther south, in particular into northern Argentina and then down into central Argentina, you can see these thrust faults, they dip in the opposite direction mostly. They involve basement, so these gray rocks are basement rocks or previously deformed sedimentary rocks. And so they look very different than your typical fold thrust belt like I was showing you earlier. These different geometries also affect the type of hydrocarbon system that's been developed within the thrust belt. And so mostly hydrocarbon systems are best preserved at the frontal part of these fold thrust belts. And indeed, there's a pretty good one over here in southern Bolivia at the frontal part of the fold thrust belt. But if you go down into northern Argentina, where you have this basement-involved thrusting, there's a poor hydrocarbon system, and it gets worse as you go farther to the south. And there's an asterisk on that. Because current exploration is actually kind of exploiting a totally different part of the geology down there. You can ask me a question at the end if you're interested. Going up to North America, we see very similar things. So we see to the north in western Montana, you can see it's a wedge-shaped thrust belt. Most of the thrusts dip toward the left, very similar to what I showed you earlier, which is similar to westernmost Wyoming down here in southeast Idaho and western Wyoming, very similar. But if you go farther to the east, so here's a cross-section by Ursula and students, you can see that the thrusts are irregularly oriented. They involve basement rock, and they look very, very different than these other thrust belts that I've been talking about previously. So I'm going to define these two different types of thrust belts. I'm going to define these ones that involve detachment above the basement and stacking of these thin layers of sedimentary rock. I'm going to call that thin-skinned. And so you can just imagine there's a thin layer of sedimentary rocks that's progressively stacked on top of each other to accomplish crustal shortening. And so you notice in this thin-skinned style of thrusting, there are thin, closely spaced thrust sheets. So these are relatively close together. If you look in map view, they're really linear in map view. They're pretty closely spaced. they always form, the faults always form within weak sedimentary layers. And so you can see that in this example right here. All these rocks are detached from basement along a really weak sedimentary layer at the bottom of the cross section. All the faults generally dip toward the interior of the mountain range. And these are really efficient at accommodating shortening. So these are the big, big thrust belts that we think of on Earth, like the Himalayan fold thrust belt. We think accommodated upwards of 600 or 700 kilometers of horizontal crustal shortening, basically by this kind of a thin-skinned structural style. In contrast, what I'm going to call thick-skinned thrust belts, they have, and here's an example, a cross-section across the Wind Rivers in western Wyoming. And what you can see is that this thrust belt, the fault orientation, so this is west and this is east, or southwest and northeast over here. So you can see that this involves basement. The fault is dipping in the opposite direction. The thrusts are generally spaced far apart in map view. If you look in northern Argentina, you can see in map view the thrusts are much more irregularly oriented and spaced farther apart. They often carry basement rocks, which is different than these thin-skinned thrust belts. And they often reactivate older structures, older weaknesses within the crust. And then these generally accommodate low shortening magnitudes. These aren't very efficient at accommodating crustal shortening, so there's very low crustal shortening magnitudes. And if you can imagine, this is kind of a zoomed in view, but you can imagine trying to characterize one of these as a wedge-shaped sandbox. It's impossible to do because the thrusts dip in the opposite direction. They're really far apart from one another. The sandbox analogy, the critical taper model, isn't a very good way of understanding these thrust belts. And furthermore, they oftentimes reactivate older weaknesses in the crust. And so in contrast to sand, which is just homogeneous material layered on top of itself, it doesn't have any pre-existing weaknesses in it except for the basal part where it's on top of whatever the substrate is. So this is not, you can't model this as a sand wedge because it has all these older weaknesses in it. All right, so I'm going to focus on two areas where there's transitions in structural style from thin skin to thick skin. And so the first one, so these are both oblique Google Earth images. That I wish I could have that view someday. But what you'll notice here's North America. So here's southern Canada, Alberta, western Alberta. You see that there's generally linear mountain ranges, linear continuous mountain ranges that are characterized by this thin skin style of shortening. And they transition down here to the south into Wyoming and Colorado and Utah in southwest Montana. They transition into being much more irregularly oriented and not linear like these ones to the north. The same thing happens in Bolivia. So Bolivia, here's the Argentina-Bolivia border. You can see these are much more linear up here. And this is where it's the thin-skinned portion of the thrust belt. And it transitions southward into much more irregularly oriented thrusts and basins in between these thrusts are spaced far apart. So there's two main things that I'm going to investigate with this talk. One is why are these transitions that are basically parallel to the mountain range? What controls those transitions parallel to the mountain ranges in the structural style? And in this case in here, southeast Idaho, western Wyoming in here, why in this case is there an eastward transition from the thin-skin structural style into the thick-skin structural style? So those are the two themes I'm going to talk about during this talk. And I won't pretend to be the first one that's worked on this because there's been a lot of people that have come before me. And I'm just going to talk about a couple ideas as to why these transitions occur in these localities, and I'm going to tell you that I think they're wrong. And I'm going to tell you why I think I'm right. But I think this one is partially right. So I think this is a really useful way of thinking about mountain belts. So this first way that I'm going to talk about, it was fundamentally trying to understand, like over here, you see in Idaho and western Wyoming, you see how the thrust belt, all these black things in here, the thrust faults seem to extend farther out toward the east than they do in southwest Montana and near the Uintas, southeast of Salt Lake down here. So this right here, this is called a salient. And so this feature right here is called the Wyoming salient. And so people have sought to understand why the Wyoming salient formed in that pattern. And one person, and there's a lot of people that have thought about this, in particular for this area, Crosby in the 60s, published a paper that basically proposed the same thing, but some more detailed work by Marshak and others has expanded upon this hypothesis. Basically what they did is they said, okay, thrust belts are sandboxes. How can we explain the shapes of these thrusts by these being sandboxes? And so they said, okay, let's explore the possibility that changing the thickness of the sand in the sandbox could explain the shape of this thrust belt. And so it makes a lot of sense, because if this is all sand here in this thin sand layer right here, and this is all the same type of sand up here, you'd expect, because they have the same mechanical properties, the thrust would have the same dip angle. And so what you'd expect is that if the thrust is forming in this thick sand wedge, it has to travel a larger distance to get to the bottom of the detachment surface. And so at the surface, you'd expect to see a wider thrust belt. Whereas if you have a thin layer of sand in here, the thrust is dipping at the same angle, but it has to travel a shorter distance to get to the bottom, and so you have a relatively narrow thrust belt in map view. And so this idea suggested that, like the Wyoming salient, is actually just a reflection of having thin basin sediments in the north and south, and then thicker basin sediments in the middle. And so that reflects this whole critical taper model, and could explain why the Wyoming salient has that geometry. And I've thought about this a lot, in particular during my work in South America, but then more recently in my work in North America. And one interesting thing is that people around this part of the world know what the belt basin is. And Paul Link was here a little while ago talking about some class in the conglomerates around here that may have been derived from the belt basin. But what you might know is that actually turns out one of the thickest accumulations of sedimentary rocks in North America occurs right along the Idaho-Montana border and into western Montana. And so this is the boundary, the northern boundary of the Wyoming salient. So describing that as an area of thin stratigraphy didn't really make much sense to me. So likewise, if you go farther to the south into the Uintas, what you'll see is that there was actually, during the early phases of rifting of North America, of Rodinia, at about 750 million years ago, there was actually a little rift arm that started to continue up here into the Uintas, and there was a hole in the ground, and 5 to 7 kilometers of sediment were sitting in that hole. So it's actually also a relatively thicker location of sediment along the western North American margin. So it doesn't seem that basin sediment is a good explanation, at least for the boundaries of the Wyoming salient. Going down to South America, there's other workers that have suggested the same thing, and they've shown that in Bolivia there's a much thicker section of sedimentary rocks, and as you go farther to the south, and this is kind of a Shazam line in here because it's kind of uncertain why, it's like basically some of it is metamorphosed. Where does it become basement and where is it sediment? But what you do see is that this is thick up here and there's a relatively thin sedimentary cover down to the south. So people argued that this was also a basin thickness control. And it turns out, just like in North America, there's a basin that's about 850 to 600 million years old that formed in this same locality. And granted, these rocks were deformed, and I'll talk about this a little bit later. But this is also a locality of relatively thick basin sediments, but they were classified as basement because they had pre-existing folds in them. So I also argue that in South America, basin thickness isn't the primary control on the shape of the thrust belt. Another hypothesis is that what I call the impingement hypothesis. And this hypothesis suggests that perhaps, and you can see in this Buettner image over here on the left, perhaps the thrust belt, the thin-skinned thrust belt, as it was propagating to the east, started to impinge upon some older basement-involved or thick-skinned structures outboard of the thrust belt. So you can just imagine this as a snowplow or a freight train or something continuing to the east, and it's just encountering these obstacles. And that in the thrust belt, the shape of the thrust belt is literally mimicking the shapes of those obstacles that it's impinging upon. And so there's some more recent work that's been done on the extent of influence of this impingement, and it does. Here's an example from right around here, adjacent to the Gros Ventre. What you see, and this is work from Yankee and Weil in particular, what you see is that these are the shortening directions. So the direction that shortening was accommodated by these rocks. So what you notice is that there's a deflection. So we'd be looking for a deflection adjacent to the frontal part of the fold thrust belt. And they do see a deflection, but it doesn't seem to continue far into the interior of the thrust belt. And if you reconstruct the kinematic history of the thrust belt, so the progressive deformation of the thrust belt, it seems like, according to Yankee and Weil, the thrust belt had initial curvature in it. And so the curvature in the Wyoming salient doesn't seem to reflect impingement primarily against these basement-involved thick-skinned structures. All right, so my students and I have collected some information, some data to try and understand perhaps the timing of these thrusts can tell us something about when the curvature was established in the thrust belt. So what we did is we used low temperature thermochronology, and basically what we use is a system called uranium, thorium, helium. And so uranium and thorium, they decay radioactively. They're unstable isotopes. They just decay radioactively down to more stable daughter products. And during that decay process, they eject a helium particle. And so what you can do, turns out helium is a gas. As you all know, helium is not very strongly retained in many of these mineral structures. And so at high temperature, the helium is produced during that decay process, and it just easily escapes the grain. However, when you cool it down slowly enough to low enough temperatures, it will start holding onto that helium in the grain. And that's what we want. When we can measure the amount of parent, radioactive parent, and the amount of radiogenic daughter, we can use that to calculate, if we know the decay rate, we can calculate how long it took to produce that daughter product in the minerals. So we use that system here. We used apatite and zircon, and we think that this cooling happens, the cooling that eventually results in holding on to that helium, that happens in the hanging walls of these thrust faults. So here's a thrust fault right here. Here's some temperatures you can see in here getting lower, closer to the surface, which makes sense. And mountain ranges, fundamentally, they're forming these topographic highs, and they're locations of enhanced erosion. And when we erode material, we bring other material closer to the surface, and it cools as it gets closer to the surface. And so thrusting, we think this particular isotopic system, uranium, thorium, helium, and apatite and zircon, we think that these ages are recording the time that the thrusts were active as the cooling was happening during erosion in the hanging walls of those thrust faults. And we collected a bunch of data and compared it to pre-existing data from southeast Idaho and western Wyoming. And I'm not going to talk about this data in too much detail, but what I want to point out is that you can see that there's along the trace of these faults, which have a northwest trend down here, you can see that the ages are roughly similar to the ages that were obtained from southeast Idaho and western Wyoming. And this, to me, suggests there's interesting ages down here, 100 million year old ages, getting younger to the east generally. But this suggests to me that some of the curvature in the thrust belt was here prior to the frontal part of the thrust interacting with those thick-skinned structures on the margins of the Wyoming salient. So I think this is another piece of evidence that suggests that the impingement hypothesis is not the fundamental reason why there's a change in the shape of the fold thrust belt. Now, if you zoom out and you look at whole Western North American scale, ages of the timing of thrusting, what you can see in southern Canada, so shown in this green shade in here, and this is compiled from a bunch of different data, what you can see is that the ages of thrusting are generally 110 to about 90 million years old in the interior part of the thrust belt. So that's Cretaceous time, mid to late Cretaceous, actually early to mid Cretaceous time. And then it generally gets younger at the frontal part of the thrust belt. So here, just like in South America, where we have those closely spaced thin-skinned thrusts, the frontal part of the thrust belt is younger. Here in southeast Idaho and western Wyoming, these thrusts are similar in age to the thrusts in western Alberta. But you see this interesting transition to where these structures on the east side, that are these irregularly spaced, thick-skinned structures, you see that these are generally younger than the structures that are in the interior of the thrust belt. So, and you see that these structures were active at the same time as these thrusts with a different structural style, that thin-skinned structural style in western Alberta. Okay, so in North America and South America, actually, people thought, there's a paradigm, still a very dominant paradigm, that suggests that the transition in structural style from the interior to the exterior part of the thrust belt, so here's North America right here, kind of a bubbly cartoon, but you can see here's the thin-skinned thrust belt shown in this kind of dark gray blob in here, and here's this thick-skinned, what they called the Laramide, thick-skinned thrust belt. And what people noticed, in particular in South America, and it was pointed out, this analog by Jordan and Allmendinger in the mid-80s, they noticed that that from geophysical data, there seemed to be a shallowly subducting plate beneath central Argentina. So it had a much lower subduction angle. So normal subducting plates are kind of like this, and this plate was much shallower and rubbing against the overriding plate. So they hypothesized that this transition from a steeply dipping subducting plate to a shallowly dipping subducting plate, along with a shift in the location of the magmatic arc, the volcanic arc on top of the overriding plate, as well as the distribution of thick-skinned structures, that reflected a shallowing slab. And so the shallow subduction angle effectively, people argued, pushed the location of deformation farther to the east, and there was more coupling, frictional coupling at the base of the overriding plate over here on the east side in Argentina relative to the west side. People looked at this and they said, okay, look at the structural style in North America. The magmatic arc also seems to have shifted its location. We think this in South America is a really good analog for North America. And there's a couple things you notice on here. This is a really broad region, 500 kilometers right here. This is a 1,000-kilometer width of this distribution of shallow subduction that they argued. And that was from pretty limited data early on. If you look in more detail from some more modern geophysical data, you find that the modern distribution of shallow subduction is more of a finger shape. And it's much more localized in its distribution. And here's kind of a 3D image showing that. So it's only a few hundred kilometers wide. And so in contrast to the prior model, which suggested a really, really broad distribution of shallow subduction, which seemed to match the distribution of thick-skinned thrust belt structures. In contrast to that, this narrow distribution of the shallow slab suggested that the active thick-skinned deformation that's happening in northern Argentina is actually more than 500 kilometers away from the location of shallow subduction. So it doesn't seem like, with our new understanding of the distribution of the shallowly subducting slab, it doesn't seem like that's a good way to explain that thick-skinned deformation in northern Argentina. There's some other really good examples that I haven't worked in particular, but some really good examples where shallow subduction does not produce this transition in structural style. For example, in the Tian Shan in China, you see that there's this thick-skinned structural style, but the Himalayan collisional belt actually has a plate that's dipping beneath India. And so there's no possibility that there's a shallowly subducting slab on the other side, on the north side of the Tibetan Plateau. So it's impossible to call upon a shallowly subducting slab. It has to be something else. So this is the more controversial part of my talk, because this is the paradigm, is that shallow subduction, thick-skinned deformation is a signature of shallow subduction. And I'm going to argue that I don't think it is a signature of shallow subduction, but I do think that there is alternate evidence that there was shallow subduction in some places. So sometimes they do match. All right, so here's the two areas I'm gonna focus the rest of my talk on. I've kind of intermediately been talking about these. But I'm gonna focus on these two areas where there's a transition in structural style. So here's Bolivia transitioning southward to this thick-skinned structural style. Here's North America, thin-skinned up here, thin-skinned in the interior, transitioning into central Wyoming, west central Wyoming, into this thick-skinned structural style. And one of the really important observations that my colleagues and I made when trying to understand what some of the alternate factors were that were controlling the thrust belt was that if you look within the Wyoming salient, so again this region that seems to extend farther to the east than much of the rest of the fold thrust belt, what you see is that the basal detachment horizon, so the rocks that the thrusts are utilizing at the base of the thrust belt, they're nearly always detached within these weak shales of the Cambrian Gros Ventre formation. And so you see within much of the Wyoming salient, this Cambrian décollement, typically the Gros Ventre formation, this forms a basal detachment for much of the fold thrust belt here within the Wyoming salient. But if you go into the Uintas and south of the Uintas and into east central Idaho and southwest Montana, the thrust belt does not utilize that detachment horizon. And I thought this was a really interesting observation. I think it tells us what the important factors were that were controlling the shape of the thrust belt. So I'm going to show you a couple cross sections in here which show that progressively farther to the south, within this Wyoming salient, you also get lower magnitudes of shortening. So here's a cross section on the north. These are cross sections by Royce. Cross section on the north and the central part of the Wyoming salient. There's quite a lot of shortening in there, about 105 kilometers of shortening, probably a minimum estimate. Transitioning farther to the south, the shortening magnitude gets lower and lower and lower. And I think it's interesting that as that Cambrian detachment horizon is less utilized to the south, the shortening magnitude also decreases. Now I'm going to zoom in on both ends of the Wyoming salient and tell you why I think that there's an alternate explanation for the shape of the salient and indeed the change in the structural style. So I'm going to zoom in up here into this place in east central Idaho that you see is labeled as the Limb High Arch. So here's a map, a geologic map of the Limb High Arch. And so Salmon, Idaho would be kind of just north, off the left north side of this diagram right here, this map. And what you see, a really important observation, is that here, instead of having a really thick, up to 7 kilometer thick stratigraphic section of rocks that are basically 750 to 500 million years old, there's actually 0 of those rocks. And what happens, if you look on here, shown as pink, sitting on top of these light blue rocks, these pink rocks, these are middle Cambrian sandstone, or middle Ordovician sandstones. It's called the Kinnickinnic Formation. And these are overlying stratigraphically, just in simple depositional contact. They're overlying 1.4 billion-year-old rocks of the belt supergroup. So those are also those fine-grained sedimentary rocks I mentioned earlier in the talk. So I was pretty interested in if this is truly a depositional contact and what the structural style was in this area where there was no Cambrian detachment horizon. So my students and I zoomed in over here and we did some mapping across this thrust in here. This is called the Poison Creek Thrust. And I'm just going to show some cross sections in here. It's a little tough to show a detailed geologic map in a presentation, but what I want to convince you is, I'm going to convince you of one thing and then I'm going to convince you of another. So be prepared. All right. So this is a thrust fault. So that made a lot of sense. It's called the Poison Creek Thrust. What you see is these rocks that have the Y in front of them. That means Mesoproterozoic, 1.4 billion-year-old sedimentary rocks. And these are sitting on here. You can see there's a thin sliver of these pink rocks labeled as OK. And that's those middle Ordovician sedimentary rocks, those sandstones. So those are basically 450 million years old. So there's about a billion-year-old time gap between the rocks in the hanging wall of this thrust fault and the rocks in the footwall right here by this Kinnickinnic quartzite. And so that's clearly, thrust faults, I told you at the beginning, they accommodate crustal thickening. So they put old rocks on top of young rocks. So this makes a lot of sense. It puts old rocks on top of young rocks. And indeed, if you look in the field, some field observations, trying to figure out which side moved relative to the other side, so kinematic indicators we call them in structural geology, they also show a thrust sense of displacement. And in thin sections, so this is a microscopic view of some rocks. Here's 100 microns for scale. You can see these also give a thrust sense of displacement. So here's where I convince you the opposite. So the interesting thing is, despite the fact that it's clearly a thrust fault, if you look at the age of these 1.4 billion-year-old rocks over here on the left side that were displaced upward relative to the lower side, the rocks that underlie the Kinnickinnic quartzite are actually older. These YS rocks are actually older than the rocks that are in the hanging wall in here. So we know that it's a thrust fault, but the displacement of those Mesoproterozoic rocks, the 1.4 billion-year-old sedimentary rocks, is more consistent with a normal sense of displacement, like a normal fault. And so we were trying to figure out what this meant, and what we think it means is that this fault used to be a normal fault and was reactivated as a thrust fault. And so as and this thrust fault, this normal fault predated Middle Ordovician time, so we think it's probably related to breaking apart of the western side of North America. And as the thrust belt propagated into that part of east central Idaho it just had this pre-existing weakness, and it just reactivated that pre-existing weakness. So this reactivation of a pre-existing weakness, this is very similar to what I described earlier as this thick-skinned structural style. And this is kind of what it looks like, and this is common in South America. And so I've worked down there in northern Argentina, and what you see is that sometimes in these thrust hanging walls, you have a little depth center that's Cretaceous in age, at least in South America. And what you know is that used to be a hole in the ground, and so this used to be a normal fault, and eventually it was reactivated as a thrust fault. So I'll talk about that in a little more detail in a second. All right, so zooming down to the southern end of the Wyoming salient in the Uintas. So this is a map that I don't expect you to see any detail on. But what I do, it has some pretty colors. But what I do expect you to see, I'm just going to point out some of the simple relationships. And the point is just to show these are really simple geologic observations. You can see here's a Psarica thrust on the northern end of this the Uinta uplift. So this is one of those thin-skinned thrust faults that's part of the Wyoming salient. And what you see here, here's the Uintas. You see this is just southeast of Salt Lake City. If you're to look at this stratigraphy down here, you have Cambrian sedimentary rocks just sitting right on top of older Neoproterozoic rocks. So that relationship is just consistent with continual deposition through time. And so that's very similar to what we see along much of the margin. So during rifting in western North America, you had a hole in the ground, and you just continually filled it with sediment all the way basically until Permian time, so 250 million years ago. So that makes a lot of sense. The problem is if you go over here on the east, what you see are Mississippian rocks of the Madison group overlying Proterozoic Uinta mountain group. So in that place, you have these 750 million year old Uinta mountain group rocks, and then you have Mississippian rocks sitting right on top of it. That's basically 300 million years of time gap between the overlying rocks and the underlying rocks. So that suggests that there was an erosional event prior to Mississippian time that eroded all of the stratigraphy below the Mississippi and all the way down to those rocks of the Uinta mountain group that are roughly 750 million years ago. And importantly, what I want to point out is that the absence of this efficient Cambrian gros ventre and correlative formations, I think is explained. So the erosion of that it could explain why this is the southern end of the Wyoming salient. So in other words, for both okay, I'll talk briefly about this. So this erosional event, we're pretty sure it's from a minor mountain building event we call the antler orogeny, and that was in Devonian time. But basically what happened is there's this broad kind of east-west trending zone. In Utah they call it the Tooele Arch. And this broad zone actually resulted in erosion of that Cambrian detachment horizon. And I think the erosion of that Cambrian detachment horizon explains why the thrust belt curves farther to the southwest on the southern end of the Wyoming salient. So in both places, I hope I've shown that the boundaries of the Wyoming salient appear to correlate with an absence of that really efficient detachment horizon, that Cambrian shale, those weak sedimentary rocks. And so here in the north, this is called the Limhi Arch, and so here's a paleogeologic map, a paleogeographic map showing that there's no sediment deposited there near the Idaho-Montana border. And then down here on the southern end of the Wyoming salient, in the Uintas, you actually had erosion of that Cambrian shale. Okay, so is it true in South America too? Yes, I think it is true in South America too. And essentially what you see in South America is that in Ordovician time, so 450 million years ago, something like that, what was present, there was a big mountain range down here, and they call it, in South America, they call it the Trans-Pampean Arch. And in Ordovician time, the pre-existing Cambrian rocks were deformed and folded, and there was a lack of deposition of the efficient detachment horizons in the Bolivian portion of the thin-skin fold thrust belt. So in other words, you had in Bolivia, which is just north of this little squiggly line right here, you had these efficient detachment horizons that the thin-skin fold thrust belt just glided along and formed this nice wedge-shaped fold thrust belt. But farther to the south, you had a highland, a topographic high area, and that those rocks were not deposited, and the older rocks were deformed. So there was no efficient detachment horizon in the south, and that's what I suggest is reflecting the transition in the structural style. You'll also see in Argentina, you see this kind of odd shape of the mountain ranges down here. If you were to look at the distribution of old Cretaceous and Jurassic normal faults that were actually formed during opening of the South Atlantic, there was a little rift arm. Sometimes rifts, they think they're gonna pull apart in one spot, and then they decide to pull apart in another spot. And that's what happened down here in South America, is that there's a lot of normal faults that started to form in Argentina and started to go up into Bolivia, in the western Bolivia, but they never fully accomplished rifting. Instead, rifting was shifted to the South Atlantic, and then that formed an ocean basin. And what you see is the thrust belt mimics the shapes of those older rift faults. So as the thrust belt was migrating along, it was propagating to the east and consuming this crust that had these pre-existing weaknesses in it. It just reactivated those older faults. And so you can see that here's an older epicenter. So right here in the hanging wall of this fault, this is a normal fault that has now been inverted. And now you have old rocks thrust upon younger rocks. And so it's an older normal fault that's been inverted as a thrust fault. You also see not only is the shape of the thrust belt controlled by this, but the timing of the propagation of the thrust belt is also controlled by this. And so this is some more work that I've done. I'm not going to spend too much time talking about it, but it's also using this low temperature thermochronology method to constrain the timing of thrusting. And what you see from these progressively deformed cross sections, so here's the modern view of what they look like. Here's the ancient view prior to deformation at the top. You can see that the earliest phase of deformation occurs adjacent to one of these rift faults. And then deformation migrated to the west. It jumped again to the east, and then migrated to the west, and then it jumped again to one of these pre-existing Cretaceous rift faults and migrated toward the west again. So I think that not only did these pre-existing weaknesses, these rift faults, control the shape of the mountain belt, they also controlled the timing of the propagation of the mountain belt. All right, so I'm just going to wrap up now. And here are the lessons that I think we can learn from looking at the northern Rockies as well as the central Andes. So we already know that mountains generally grow toward the continental interiors, and toward the interior of the South American continent. So this is getting younger and younger progressively toward the east. We already knew that. But what happens with continued deformation as the thrusts continue to propagate into that continental interior, they're going to do one of two things. The first thing they're going to do is they're going to, probably that continent that you're concerned about was a pre-existing rift margin. And there was a pre-existing thick section of sedimentary rocks that was deposited along the rift margin, just like is happening now on the east coast of North America. So a passive margin. Probably it was like that. So there'd be efficient detachment horizons parallel to sedimentary bedding that the thrust belt was going to utilize. But as this clicker is kind of happy. As you continue to migrate toward the east, you're going to run out of detachment horizons as you get farther onto the continent. And instead what's going to happen, like in this Argentina example, is that alternate weaknesses are going to be reactivated. In South America, and much of this portion in Argentina, the pre-existing normal faults were those pre-existing weaknesses. But there are also other areas. So here's another example in Argentina where there was a pre-existing weakness that was not an older normal fault, but instead was a strong layered fabric within the metamorphic rock. So a strong metamorphic foliation that seemed to have been exploited during deformation as the thrust belt migrated through there. There's examples in southwest Montana, in particular by Chris Schmidt and his students, that shows that dikes, so these tabular intrusive igneous bodies, were also reactivated. So in some places you can see that these dikes intruded and they were reactivated as thrust faults as the thrust belt migrated through there. And then at the example that I gave you before, these rift faults, especially in South America, are also reactivated as weaknesses. So I think, what I'm going to argue is that all thrust belts fundamentally prefer to utilize existing weaknesses rather than forming new faults. And I think this fact is really important in explaining the transitions from thin to thick skin structural style. In thin skin fold thrust belts, there's pre-existing bedding that the thrust can exploit. And so the thrust form parallel to these pre-existing sedimentary layers, stack these thin thrust sheets on top of each other, and accommodate a lot of shortening. But if there aren't any of these sedimentary layers to exploit, the thrust belt will activate alternate weaknesses, and those could be pre-existing faults, they could be a foliation, they could be dikes, they could be any number of things. And so this is a quote from one of my colleagues who, I really like the quote because it kind of sets a scene, but basically what we're doing in these fold thrust belts, we're taking all this material over here and we're feeding it into the fold thrust belt. It's kind of a reference frame issue. And you can think of old continental crust. It's had a long protracted history, and so it has a lot of pre-existing weaknesses in it compared to a relatively undeformed stratigraphic section. And so the shape of the fold thrust belt depends. It's like a meat grinder, so what you put into the meat grinder dictates what you get out of the meat grinder. So that's kind of the conclusion of my talk. Thanks. Yep. And I'm happy to answer any questions if you have them. Yeah?
Perhaps this is getting a little too technical, but originally you mentioned the tapering model, and you said the Coulombic, meaning the frictional interaction. And now you're bringing in older, younger, pre-existing, etc. Can you say that the older ones, which participate later, happen to have lower friction slip zones, and that if you put everything together and did a finite element modeling and just chose the lower Coulombic or lower frictional number, it would automatically fall out of that? In other words, using a single parameter like friction without getting into old, young, raw, pre-cooked, etc.
So can we change the strength
just
of the wedge and still model it?
Slip. Yeah, just do that and see that it changes the orientation and the slips occur without, in other words, reducing it just to a frictional interface number.
Well, I think one, it's a good question. I think that one problem, regardless of what parameters you use for the frictional parameters in the sandbox models, one problem is that there's no mechanical anisotropy in the box to begin with.
Absolutely.
So I think that's really important. I think that I'm not sure if anyone's put added a pre-existing weakness in a finite element model and see what happens to it. I mean, like the one I showed, they had the horizontal layering in there, but I'm not sure if they've shown other weaknesses in there. I do know that there are. So basically, what happens? The reason why this wedge is moving along, it builds up all this friction. It's really high, and there's a lot of friction on the bottom of it because there's a lot of stuff stacked up there. And so it doesn't want to continue slipping on there. It wants to or continue building in here. It wants to actually slip outward and form a new shape to the wedge. So there's models that show that with pre-existing basement weaknesses that basically the same thing happens, but there's just, instead of just simply incorporating material in front of it that's undeformed, instead it prefers to propagate out to those pre-existing weaknesses. So it's a competition between how much friction is on those faults that it's sliding on and how much weakness, what the friction is along those weaknesses that are in front of the fold thrust belt. So if there's less, if it's preferable to reactivate one of those, then it will. And if it's not preferable, then it'll continue slipping on these features in here. I don't know if that answers your question. No? Sorry. Yeah.
North of Wyoming, there's that Great Falls Tectonics where the two terrains have come together. So why hasn't that been activated? I mean, you would think, okay, there's going to be a big mountain range then going from southwest to northeast along that zone.
Well, that's a good question. We don't.
Can you repeat the question?
Oh yeah, sure. I'll repeat the question. So the question was, in southwest Montana and western Montana, there's a fundamental crustal weakness, which we call the Great Falls Tectonic Zone. So if these crustal weaknesses are preferentially reactivated, why was that one not reactivated? And I would say that there's not really one structure that defines the Great Falls Tectonic Zone. It's kind of a term that encompasses a lot of, like a zone. And so I'm not sure that we really, there is any specific fundamental weakness in the crust that could have been exploited. Yeah.
Going back to the sandbox, you do have a weak zone that's between the sand and the bottom. What if your shoving shelf did not go all the way to the bottom so that you were pushing sand over sand? Do you think you get the same features form?
I think so. That's a good idea, though. I've never tried that. But I think you would get the same features formed, but it would just have a little bit different. I think the critical taper theory is really useful in that, if you do change the frictional resistance at the base of the wedge, I think that will change. It's been shown to change the geometry of the wedge on top of it. So in that case, maybe that would make it a slightly stronger frictional resistance to slipping, and that would actually increase the taper angle of the wedge. But I would expect that it would do the same thing.
The other question related to that is that you showed the basin model as a shelf that was shaped differently. So if you did that, so you had thick sand on the sides, and it's just that you can play many games with the sandbox model to look at some of these other barriers.
Yeah.
Yeah. It would be fun to do in a freshman course.
Yeah. So I actually have, not in a freshman course, in a graduate level course, I just had the first assignment for my class called Advanced Structural Geology. We have a couple of these sandboxes in the basement, and so their assignment is to do a couple of these experiments and get creative with it. So maybe next time I'll suggest some of these ideas that you have for different end numbers for how, what the structures might look like if you change things slightly.
I can monopolize you for one more question. What would be the physical analog for the shove in your sandbox?
That's a really good question. We don't really know, honestly. I mean, we think that fundamentally it's probably, there's got to be some, continental mountain belts, they form at convergent plate boundaries. So there's got to be some transfer of stress from that convergent plate boundary into the interior of the mountain belt. But what is the real buttress in that? I guess it's probably, just speculating, it's probably the fact that, if you go deeper into the crust, you start to get more gooey rocks. And so when you push on those rocks, those just simply deform. They don't have any strength to them. And so fundamentally, it's the upper part of the crust, that kind of brittle fracture type material in the upper part of the crust that's kind of translating all that stress. And so I would guess that even though the plate is pushing on the side like that, there's got to be transmission of stress in that upper part of the crust that's somehow forming a backstop to all the thrust belt that's deforming in front of it. But those kind of questions are they're tough to test, but I think that understanding how stress is transferred and how the deformation style changes with depth within these full thrust belts, it's a really important question that hasn't been sorted out. Yeah.
You referred to the Grovant and the Wind Rivers as thick-skinned mountains, right? But both of those have a continuous down Cambrian strata, which should have the weak layers that you referred to.
Yeah, that's a really good point. I had a student working in Southwest Montana where we receive the same thing. There's you get basement, you get flathead, and you get a bunch of shale, Cambrian shales on top of the flathead, and I think that the reason why in those instances, so it gets back to kind of what I was mentioning before. I think that these thrust belts are reflecting deformation, brittle deformation of the upper part of the crust. And so this is why I said at the beginning, I'm going to say everyone's wrong, but I do think that the basin thickness model, there is some truth to it. And I think the reason why the basin thickness can be important is because you have to have those detachment levels down deep enough such that there's not a big wad of brittly behaving fracturable material underneath where the detachment horizon is. And so basically, if you don't have enough thickness of sediment, you're not down deep enough such that that there's enough crust to be able to deform above that ductily deforming basement on the lower part of the crust. So I don't know, was that too complicated or,
Oh, no. I mean,
or unsatisfying?
at one point, we can wave our hands and do lots of things.
Yeah.
Okay, this one's good over here. And
Yeah.
This one's
No,
good. It probably
it's
is.
a good point. I think that there is, so I think fundamentally, you know, some of those models, I think, no, what I'm trying to say is that I don't think those are fundamentally the reason why there's a transition in structural style. I think the structural style reflects the distribution of detachment horizons, but I think there are other factors that are important in influencing whether the detachment horizon is everywhere utilized. Like you said, in the Gros Ventres, and then, to be honest with you, I'm not too familiar with the geology of the Gros Ventres, but I know that in southwest Montana there are places on the northeast side of the Limb High Arch where those shale horizons are present, but they're not utilized by the full thrust belt. And I'm not exactly sure why that is, but I think it's because there's not a thick enough stratigraphic section above them to be able to accommodate enough shortening by the full thrust belt. It has to reactivate a deeper detachment within the basement in order to accommodate upper crustal shortening. So that's my complicated response.
So what is the basement fault in the Wind River, so the Gros Ventres that's being reactivated? Where did that come from?
So like I said, it's not always a fault that's reactivated. Sometimes it's other types of weaknesses, and I haven't looked. Unfortunately, I haven't looked at all of these mountain ranges myself. But what I do know is that some more recent work that Adolf Yonke has done in the Wind River suggests that in some places the fault seems to be reactivating the basement foliation, and so that's a possibility. And people have suggested, in particular, Marshak, who's the guy that did the sandbox models, he suggested that there are a bunch of rift faults that were reactivated during the Laramide orogeny. The problem is, it's very difficult to demonstrate that there were these pre-existing faults because, unlike South America, there's no rift basin developed in the hanging walls of those faults. And so it's tough to say that those were pre-existing faults when you don't have evidence that there were normal faults or anything like that. But there are areas, like I was mentioning in southwest Montana, where dikes have been reactivated, and apparently the foliation's in the metamorphic rock. But I'm not sure if all of those mountain ranges reflect reactivation of weaknesses. That would be what my hypothesis suggests. But I haven't investigated that in detail. And I'm not sure if anyone has. Yeah.
And by way of summary, didn't you kind of say that all the thin-skinned crust belts are related to younger sedimentary layers, the ones out on the west coast, and the thick-skinned ones are related to older continental crust? So there may be something about the slip of the young layers that doesn't exist in the thick. So there may be two different types of Coulombic effects, one on the younger stratified layers and the thicker ones. Is that some kind of a summary of what you said?
Yeah.
Okay, so young has something to do with it, and
Well,
old, as well as
Yeah.
location.
And young in the sense that old rocks have, they've been subjected to a lot of different deformational events. And so, and these young, quote unquote, young sedimentary rocks, they're generally less deformed. And so, in that sense,
Their interfaces are probably
yeah.
more well defined than
Uh-huh. Yeah.
And that's a lot to do with the Coulombic interaction.
Yeah,
Are we really getting into, with this young and old, to the degree of cementation, porosity, permeability, and fluid pressure?
Yeah. I don't. So this is fundamentally getting to the question of what's basement and what's not basement, and that's a question that I've thought a lot about. And what I think is really important is the orientation. So I didn't talk about this thing I teach in my introductory structural geology class. Is called Byerly's frictional law of sliding, which the term isn't that important, but basically what it means is that most rocks will prefer to slip along pre-existing weaknesses if they're in the right orientation. And so thrust faults, if there's a vertical feature and the thrust fault is trying to shorten the crust in a horizontal direction, it doesn't want to utilize a vertical feature because that's not going to do anything for it. So the structures have to be oriented in a favorable direction in order to utilize those. And so I think that some of the, in South America, there's these previously folded sedimentary rocks that I was talking about, 850 to 600 million years old. I think that the presence of those rocks, of those folds in those rocks, despite the fact that those rocks are actually sedimentary rocks, they're fine-grained turbidite deposits, which should have good detachment horizons in them, but the detachment horizons weren't favorably oriented because they had these pre-existing folds in them. And so in that sense, and this is why I said it comes down to what's basement, because that is kind of behaving like basement because it's deforming as a cohesive unit rather than slipping along these discrete sedimentary horizons. But it doesn't even have to be like that. Like in the Belt Basin, for example, in Idaho, it doesn't look like the detachments are forming parallel to bedding. And I think what it relates to is if you look at the angle, the dip angle beneath the Ordovician rocks, they're actually dipping to the northeast. So they're not dipping in the right orientation for the thrust belt to utilize that pre-existing sedimentary layers. So I think that, we can talk all day about whether these rocks are too cemented to behave like sedimentary rocks or whether they're, but what I think is most important is that the weak horizons have to be oriented in the right direction. And it doesn't necessarily matter, it probably does, how much cementation, that kind of stuff. It's more of whether these detachment horizons are present and whether they're in the right orientation. Any last questions?
So, are there any more questions?
What's happening tomorrow? What's the topic?
So tomorrow at about 12:15 at Whole Grocers upstairs, and Chris, do you want to, basically you're going to expand on what you've talked about here. There's a whole segment that you didn't have time to get into with why are there earthquakes in Soda Springs, Idaho, also earthquakes in the Gros Ventre. Do you want to add to?
Yeah, I presented much of this story now, but I can give a more technical talk tomorrow about some more of the details of this. But I was thinking of spending more time talking about the recent earthquakes, and so I've been thinking about those a lot just because there's no seismologists in eastern Idaho, so all the media call me when there's earthquakes. So I'm gonna talk about these Soda Springs earthquakes probably for most of the time tomorrow.
So on behalf of the geologists at Jackson Hole, we want to thank you for an excellent presentation.